All right, let's get into it. Today, we're going to peel back the curtain on our digital world and look at something that's kind of like its invisible skeleton. We're talking about data structures, the unsung heroes that bring order to the absolute chaos of information that powers, well, pretty much everything we do.
I mean, really think about that for a second. You hit search and boom, it's just there, instantly. Now, that's not magic, right? It's all about organization. It's because of a super clever blueprint that tells the computer exactly how to store information so it can be found in like the blink of an eye.
To really get why this matters so much, let's use an analogy. Picture a massive library, but instead of nice, neat shelves, every single book is just chucked into one enormous, chaotic pile right in the middle of the room. Good luck finding the one book you need, right? It'd be an impossible, super frustrating task. And that, right there, is what data looks like without any structure. So, the solution to this library nightmare? Well, that's a data structure. It's the shelves, the catalog system, the signs on the walls, the whole shebang. It's a way of organizing data that thinks about not just the items themselves, but, and this is the really important part, how they all relate to each other. It's the blueprint that transforms that useless pile of books into a library you can actually use.
Okay, so before we can build our digital library, we gotta understand our building materials. Data basically comes in two fundamental forms. You've got your basic bricks, and then you've got the complex buildings we actually make from them.
And this slide lays it out perfectly. Over on the left, you've got primitive data structures. Think of these as the individual Lego bricks, a single number, a single letter. They're the absolute basics, and you can't break them down any further. Then, on the right, you have the non-primitive structures. These are the cool things you actually build, the organizational systems like arrays and trees that we construct using those bricks.
And that's really where our focus is going to be. The real power, the organizational magic that makes everything tick, it's all in these non-primitive structures. These are the shells we're about to build.
So let's start with the most obvious way to organize anything, right? Just putting things one after another in a straight line. These are our first, most basic bookshelves.
In the tech world, this is called a linear data structure. And just like the name says, its elements just form a sequence. There's a first item, a second, a third, and so on. Super straightforward, just a sequential lineup.
And the most fundamental, the most common of all these linear structures is the array. If you've ever dabbled in any kind of programming, you've definitely met the array. It's pretty much the bedrock of organizing data. So what is it exactly? Well, an array is just like a numbered bookshelf. It's an ordered set, which means the position of every item matters. And what's really important is that all the items are stored right next to each other in the computer's memory. But here's the key. To find something, you don't have to search through all the items. You just go directly to its shelf number, which we call its index. That direct access is what makes it so incredibly fast.
Now, an array is awesome for just simple storage and grabbing stuff. But what if the way we add or remove data needs to follow a specific rule? What if our bookshelf isn't for browsing, but for processing items in a very particular order? And that brings us to the stack. A stack operates on this really simple but powerful principle: last in, first out, or LIFO for short. It just means the last thing you put in is always the very first thing you can take out.
The absolute best analogy for this is a book returns cart at the library. As the librarians get books back, they just place them on top of the pile. When they're ready to put them back on the shelves, which book do they grab first? The one right on top, of course, the last one that was put in. The official term for adding an item to a stack is called a push. You're literally pushing a new element onto the top of the collection, just like you'd place that next book on the cart.
And to remove an item, we call that a pop. You just pop the top element right off the stack to use it. But here's the catch. You can't get to any of the books buried underneath until you've popped everything that's sitting on top of them first. This super controlled access is exactly what makes stacks so incredibly useful for things like, the undo button in your favorite program.
But hey, not all data fits neatly into a straight line, does it? Sometimes the most important thing isn't the sequence at all, but the complex connections between all the different items.
This is where nonlinear data structures come into play. Here, the data isn't in a simple A to B to C sequence. Instead, this type of structure is all about showing relationships, hierarchies, networks. Think less about a line and more about a web.
The two classic examples you'll always hear about are trees and graphs. Trees are just perfect for representing hierarchies, like the file system on your computer or a company's org chart. And graphs?
They're used for even more complex networks, where anything can be connected to anything else, kind of like a social network or a map of roads in a city. And this right here just nails the difference. If linear structures, like arrays and stacks, are the individual bookshelves, then nonlinear structures are like the library's entire floor plan. They don't just hold the books, they show you how all the different sections and rooms are connected to each other.
So, we've looked at a few of these digital blueprints, but why does picking the right one matter so much? Well, it's because the structure you choose completely determines what you can do with your data and how fast you can do it.
Let's go back to our library one last time. We've got our shelves, we've got our floor plans, we have all these fantastic ways to organize our books. So what's the big payoff? What do all these systems actually let us do?
Here's the thing. The right data structure makes these core operations unbelievably fast. Searching lets you find that one specific book in a library of millions. Sorting lets you arrange them all alphabetically. Merging? That lets you combine collections from two different libraries without a hitch. Updating, creating, destroying, these are the basic actions that software does billions of times a second, and it's all made possible by the structure holding the data.
And that really is the big takeaway. Without these elegant, organized blueprints, everything we take for granted, from our operating systems to our social media feeds, would just grind to a halt. Our digital world would be nothing more than that giant, chaotic, and totally unusable pile of books we talked about at the very beginning. So, the next time your app runs perfectly, or you search for a photo and it pops right up, or you hit undo and it just works, just take a second and ask yourself, what cool, elegant structure is hiding just under the surface, making all of this possible? Thanks for tuning in.